Good morning, Professor.
Good morning.
How are you
Or
doing
afternoon.
today?
Afternoon.
Afternoon now.
Yes, that's right. Sorry, I was just adjusting. I have this lamp here. See if I can get my face a bit more lit up.
Are we doing reviews today?
We're continuing, yes. I had started on a test here. I believe this is the test we were working on. I'm not sharing anything right now. Keeping it all to myself. Hang on. I'll get that in a minute. Yeah, we were working on this fall 2018 test, I believe. Yeah. So I was at I had just done number 3, I was on number 4. And
I'm not gonna, sorry, go ahead.
So I'm just going to finish going through this test and then I'll leave it open to questions about anything else.
I'm not gonna stick around the whole time then. I like to use these tests to gauge how ready I am.
Okay.
Could we go over the mechanisms? I think that's the only thing I don't feel comfortable studying on my own right now.
We don't need the mechanisms for anything. You just need well, you're talking about these question 6 here. We're going to go through question 6 here.
Right there, it asks for the mechanism.
Like a mechanism
down one page.
action, right?
Oh, you mean, for number 7. Oh, we'll go through one of those anyway. So maybe you should hang around for that. All right.
All right.
But I want to get through this test here completely, and then we can leave it open to those kinds of questions. Okay.
Dr. Musgrave, I have a question.
Yeah.
For the people who have accommodations, is it going to be set up the same way as last time?
Yes.
Okie dokie.
So I'm expecting that those people will start early, like 11:30.
That's what I figured. Sounds good.
All right. Let's see. Is it 12? No, it's not quite 12:30 yet. I can't do anything yet. I'm just gonna sit here. Just gonna sit here. Yes,
Professor
Philip.
Musgrave.
Philip.
Just out of curiosity, I was looking through the laboratory, and the last item there is the last day worksheet. It just wants us to like take a picture, write our name, and sign across the page.
Well, I'll give you that worksheet, but that's only if you need it. I mean, if you remember, you can drop a lab. That could be your drop lab.
Oh,
which means you might not need to even do it.
Okay, so yeah, because I was just looking at it and I was just wondering, like, is it really that simple? Because it's like,
no, there's more to it than that.
Oh, okay.
Okay, so yes, you'll have to do something.
All right.
All right, it's going to be a bit of a surprise. I'm going to leave it as a surprise for you, Philip. So, but hopefully you won't need it. You won't need it. Okay. So let's continue on with what we're doing here. We were on this test here, and we were up to number 4. And this particular one is cis12. Somebody needs to mute, please. Not sure who it is, but somebody does. And this one here is cis12 dimethyl cyclohexane. So what you would do is draw your lightning bolt. Do that again. Okay, so then you would put your groups on, and you put your axials first. I like to start with the puckered up one first, and then alternate the axials all the way around, and then alternate the equatorials. And then I'll do cis12, which means I'll put a methyl group on this first carbon, the puckered up one, and I'll put it on the axial, but I could have put it on the equatorial, it doesn't really matter. I put it on the axial. This is cis, so it has to go here for the other one. So it'll be on the second carbon on the equatorial. Now the whole point is that they're both pointing upwards. That's what makes them cis. And then we can put hydrogens on the rest of the ones we didn't put methyl groups on. Does anybody have any questions so far about how I arrange that?
Yeah, with cis, it doesn't matter which one is pointing up or down, right? Or
Well, I mean, I could have put them. I could have put the methyl group here and here if I'd wanted to, Philip.
yeah, okay. But it only matters when you do trans.
Well, for trans, then I would have put one where I have it and then one down here. That would be trans.
Okay.
I'm sorry, I thought cis was when they're both going the same direction, right?
Relative to the plane of the ring, not when they're both axial or both equatorial. No. When they are both pointing in the same direction relative to the plane of the ring, that means both up for cis or both down.
Oh, I see what you're saying.
But that's a common misconception. I mean, that causes a lot of problems for people.
Okay, and so we know that they'd be pointing in different, they wouldn't both be axial in this one because of which carbon they're on, 1 and 2. Because if it's on the second carbon,
Right,
it
yeah,
would be having
yeah,
to go down.
that's right. Now, if it was 1, 3, by coincidence, they would actually be both axial or both equatorial, being cis.
Gotcha.
So for the numbering, could you have done them on the other side? Like, does it not really matter where
Like
you?
here, yeah, that'd be fine.
No, like on the other point, like completely opposite.
Oh, you mean like down here?
Yeah,
Sorry, here and here, or
Yeah.
here. Yeah, that'd be right.
okay.
But you really, for the sake of consistency, you need to put the methyl groups either here or here.
Gotcha.
All right, that's my advice. You don't have to follow it, but that's what I recommend. Okay, so equilibrium arrow here, and then we flip the ring to the other lightning bolt. And then again, we do that same pattern. And then we put in the methyl groups. Let's see, we'll put one. So the methyl groups have to go in the same location. I'm going to put a star on this one here. And that means that that's the star carbon there. And the methyl groups will be here and here. So what I want you to notice is that the methyl groups keep their same relative direction relative to the plane of the ring. What I mean by that is that they're both still sticking upwards.
So why would you put the second CH3 that you drew there versus on like the carbon above it?
You mean here?
Yeah,
Because in the one I drew it on, it's in the front, right? It kind of looks like the front. So it still maintains its same position. That's still the front.
Would it have been wrong to draw the methyl group in both of these on the further back molecule?
No,
Sorry, the atom.
it wouldn't have been wrong, but you have to be consistent.
Right.
Okay. Any other questions?
Just clarifying what they just asked. So in the top diagram, the top right, we're calling it position 1. And when you do the second chair confirmation, position 1 now is pointing down.
Yes,
Is that correct?
that's correct. Because what we did to twist this ring was we pulled that carbon downwards and pulled this one upwards.
All right. All right. I understand. Thank you.
So they still maintain their same position. The methyl groups are still both pointing up. They're still cis, obviously. Sometimes I get people, they'll switch the methyl down here and here, for example, and that would be wrong.
Because they're down.
Because they're down.
In the top, they're up.
They're up. Yeah, you have to be consistent. Now, if you stuck them both down to begin with, then that's what I'd expect on the second one too. It has to be consistent.
It's been a while since I looked at these, and when I went back to review, I couldn't remember where to find numbers 1 and 2 on the second confirmation. So that's what I wanted to clarify.
Are we good?
Yep, I understand.
Okay.
Thank you.
All right. Does anybody have any other questions about number 4?
It's still kind of like the same question I asked earlier. So since you're taking the position 1 and like practically flipping it.
Well, not really flipping. It's not, I shouldn't say flip. Flip's not really the right word. It's twist. I'm twisting it.
So since you're twisting it and you're putting that CH3 down, it's in the same position, but like the point is going down now instead of pointing up. Why wouldn't the second one be, I don't know how I can't explain it right. I don't know what I'm trying to, like, I know what I'm trying to say, but it's not coming out right. Why wouldn't the second CH3 be on the carbon above it in your second position? Like, I get that it's the front, but since it was on the pointed one in the first position, why is it on the pointed one in the second position?
Well, you know, the star one that I'm circling here is the same carbon, right? You're okay with that?
Yeah, I get that one. It's the other one.
Yeah, I know. So you're not okay with this being the front? What I'm circling here?
Yeah, I get it's the front, but since it looks like it's switching carbons, like it looks like it's on a different carbon.
It isn't. It isn't. I mean, the front is still the front. When I twisted this, all that happened was I pulled the ones that had the arrows on up and down.
Oh, okay.
So they still maintain. It's not like I'm flipping the ring around or anything. I'm just moving those 2 carbons, which changes the position. It might be helpful to go back and look at that video that shows the transition.
Okay.
So that you can get a deeper appreciation for why that is consistent and consistently correct.
Okay, I was just like, to me, it just looks like a mirror image, like you're flipping it across an axis.
It's not meant to be a mirror image because you're not doing that. You're not making it. You're not taking a mirror image. You are actually physically rotating bonds by shifting carbons from up to down and down to up. But that's why I say I'd recommend go back and look at the video that shows that transition.
All right. Thank you.
All right. The other thing that's important, of course, is that axial becomes equatorial and equatorial becomes axial. Now, the other question it asks is one conformation favored? And the answer is no, because both have one large group equatorial. So the dimension of large group, I think, is important. And the fact that it's equatorial is important. The large group being the methyl in this instance. And if you just said large group, I'd be fine with that. I'd know that you meant the methyl group.
Is it okay if we also mention the difference in energy as well?
Well, I don't know, I'm just trying to keep it as simple as possible here, Philip. You can add whatever you like, but the point is you definitely need to mention something about the large groups being equatorial.
What if we just said methyl if we didn't use the word large group? Would that make it wrong?
Would it make it wrong? I think, well, And I don't know if it makes it wrong per se, but I don't know. I just think the fact that it's a large group is really what matters, rather than the fact that it's a methyl. That being said, I mean, if somebody said methyl, I'd just sneer at it and then probably still mark it right. But I don't like it very much. I like the recognition. It's the fact it's a large group that causes it to be energetically favorable or unfavorable, depending if it's on equatorial or axial. Any other questions?
Does it matter which conformation you draw first?
No. Any other questions?
I do. So
Yeah.
if both groups were if both large groups were equatorial, then it would be favored.
Yes, because in the other case they would both be axial, Deanna.
Sorry, just one more clarification on that. So equatorial is going to be more favorable than axial?
Yes. And
Thank you.
if you want more information as to why that is, I suggest you go back and take a look at the video for that. Okay, because I do go through that. All right, any other questions? Okay. Did I do this one specifically before as an example? I can't remember.
I think you did.
I think I might have. I'm going to pull up another test here. I think I do remember doing that one. Yeah, Jonathan, I know you hate this because it's almost like I'm spoiling the surprise for you because you want to use these tests, but well, tough titties is all I can say. I'm sorry.
It's all right. I feel all right about this question in particular, so no worries.
I probably shouldn't use that expression. I'm sorry, it's an Australian expression. It actually isn't supposed to be crude, but I'm sorry. I don't think it translates very well. I apologize. Yeah, okay. I don't think I've done this one. Maybe, I don't know. Maybe I didn't. I'm doing this one. My recommendation for these would be I'd do it out as a line structure and as a Fisher projection. Okay, so H, NO2, and then looks like it's going to be 1, 2, 3, 4 on the bottom, and then 1, 2, 3, 4 on the bottom as well. Okay, BR. I don't know. I think it's easier. And you're going to be less prone to making errors, I think, if you do this. Does anybody have any questions about how I express that as a line structure? So I'm going to draw this twice now with the lowest priority groups in the back, which means putting the hydrogens in the back. In order to do that, let's see, move that one, the hydrogen to the back, moves the butyl group over onto the right and the NO2 over there to the left. Now notice how I kept the nitrogen connected to the C. I didn't make it NO2. I made it, I didn't put the oxygen there. I put the N there. I want to maintain that. Hydrogen goes down here. And then the butyl group goes over here on the left side, and the Br goes over on the right. So I'm going to repeat that. Whoops. I'm going to repeat that same structure down here. We're going to handle the tops and bottoms separately. See, by doing the line structure, I'm not going to make any silly mistakes about where the C is connected over here, the one I circled. All right, any questions so far about what I've done?
Not a question, but any tips about not doing too many lines? Sometimes in all the CHs, and then especially when they're with the front and back, I have a hard time keeping track and making sure I have enough and not too many. It seems like I always add one extra CH2 in there.
Well, you're just going to have to be more careful, Rebecca. I'm sorry.
But is there any way? I mean, I've been trying to put like C's at the junction.
Well, I mean, I would. What I do is I look at the initial structure. Can you see my cursor?
Yes.
Okay. 1, 2, 3, 4. So I count 4 carbons there. And
Okay.
I walk myself over here. And I go 1. Sorry, I'll go 1, 2, 3, 4.
Okay.
That's all I can really do.
Okay. All right. Thank you.
All right. So let's look at the top one first. And the priorities, let's see. The NO2 gets the priorities, number 1. And then this grouping down here will be number 2 because it's got the C connected to the Br. And this is C connected to C. So that would be number 3. So it goes N, C, C, N, C, C, no winner. And then the C is connected to a bromine and the C is connected to a C. So that's how we decide between the 2 and the 3. Does anybody have any questions? Okay, so the configuration is it's 1, 2, 3. Looks like it's counterclockwise. So that would be S. So top S. And then we look at the bottom. And we've got, let's see, 1 would be the bromine, and then the grouping here with the 2, because it's CN, and then we've got CC down here, so it's 3. And that looks like it's S as well, so the bottom is S. Okay, any questions? So everybody's hunky-dory with that, huh? All right.
So why is second priority on that carbon versus the one with the 2 bromines on it?
Because we never get to see the 2 bromines. Because what happens is, remember, you only go out 1 atom at a time. So you go Br, and then it's C, and C. All right, so now it's between C and C. And then I ask myself, well, what's the heaviest atom attached to this C? And it's N. And the heaviest atom attached to this C is another C. So the one with the N wins.
Oh, okay. Thank you.
All right, any questions?
Yes, for the top one where it
Mhm.
says number 1, is that should that be NO2 or like why does it say NO1?
It doesn't. It's O2N, actually.
Oh, okay. I wasn't quite sure.
All right?
Hey, Musgrave.
Yeah.
So I understand this whole concept, and on the test I understand it, but when I went to do the quiz for it, I feel like I was doing it completely wrong.
Well, were you getting the wrong answers?
I was getting the wrong answer every time, but I was confident when I was doing it because I was doing it the way I did on the test, I guess. I wasn't sure if maybe there was a different format that I should be following, or maybe I'm misunderstanding the questions on the test. Or
That would have to be something I'd have to look at individually for you.
No worries.
Okay, I can't really diagnose that here, but you know, we can talk about it. If you send me specific examples, and you know, I can correct where you might be going wrong with it, possibly.
Okay, thank you.
All right, so let's look at the name now, and somebody had put in chat a suggestion for the name, but the suggestion had R's and S's in them, but it's going to be just S and S because they're both S. But let's draw this out as a line structure. All right, let's have a look. So to draw the line structure, count the carbons, and let's see, I get 10. And it makes sense that it's 10 because you've got 4 on the bottom and 4 on the top. You can see that. And then you've got 2 in the middle. So 4 plus 4 plus 2 is 10. So yeah, it is just a decane. So what I do is I leave the backbone, you know, which is these two carbons here, the same. That makes it a little bit easier. And just ignore the hydrogens because it is a line structure. And then just draw off the same things, just ignoring the hydrogens. I don't know, maybe you might like doing that, maybe you might not, but that's how I do it. And then I can number it, and I know I'm going to have to number it from the bottom because that's the busy end. That'll provide the lowest possible numbers. Okay, and I'll look at the chat in a second, see what's going on with that. Okay.
Did we do it that way for letter D on the test, the way you just did it?
Do you have to do it that way? No, absolutely not. This just makes it easier, I think. I don't care as long as you get the right answer. Keisha, you can do it standing on your head for all I care, as long as you write down the right answer. But this is the easiest way.
Thank you.
Does anybody have any questions? All right, so as you can see, specifically 5 here is the bottom, and 6 here is the top when we talk about the chiral centers. So I think that's useful as well, because then you don't get them mixed up. And then when you put the name in, it would be, let's see 5S and 6S. So it'd be 5S, 6S. See, that would be especially important if one was R and one was S, because it would be wrong to mix them up. So 5S, 6S, and what have we got? 1,1,5 tribromo, 6 nitro. 1,1,5 tribromo. And 1,1,5 tribromo would be incorrect because you have to say that they're both on the 1. So that's why it's 1,1. And then 1,1,5, not 6 nitro decane. Does anybody have any questions?
Yes, so how do you know that 6 and 5 are the top and bottom?
Because I had to number from this carbon with the BRs on it, Philip. which meant that was 1, 2, 3, 4, as you can see, which made the bottom one 5 and the top one 6.
Okay.
And so it's all determined by where you number from.
Does them being top and bottom matter really, or is it just a way of identifying which one's which?
Completely arbitrary. I just like to do top and bottom because it's easier for me to keep my stuff straight.
Gotcha.
You don't have to do that, but I think it's easier.
Sure.
All right. Anybody got any other questions?
Just to be clear, for the stereochemistry, the 5S and the 6S, it goes by number.
It does. Yeah, it goes by by number. So that's numerical. You're right. So if there was an R and an S, you wouldn't put the R first. It goes by number. All right. Any other questions? So we need an enantiomer, and to get the enantiomer, I'm going to look at the bottom one here, which doesn't matter. Remember, it's the same as the one above it, right? But I've got the name next to that one, so I'm just going to do this. All right. So this is going to be the enantiomer. And to get that, I'm just going to do a straight mirror image. All right, and that's going to be a 5R, 6R, yada, yada. You can yada, yada all you like as well, as long as you've done it once, and you don't have to do it again. Okay, you don't have to put the name in again. I'm interested in your interpretation of what the stereochemistries are here. Any questions?
If we would have did the mirror image of the original one, would it have been wrong?
No. Understand though, you haven't changed. By rotating the lowest priority group into the back, we haven't changed the stereochemistry. So you could just do that structure at the outset, the one we did at the beginning, yeah.
Okay.
Any other questions so far? All right, we also need a diastereomer. Now the diastereomer could be, you can either get it from the original or you could get it from the enantiomer. It doesn't really matter which. Now I'm kind of running out of space here, so I'm going to erase this name here. I'll just put 5S. 6S, just to remind myself of the stereochemistry. So that was the enantiomer. Let me write enantiomer down here. And then this is going to be the diastereomer. I'm just going to do it based on I'll do it based on the enantiomer just for kicks. So I'll leave the enantiomer the same. I'm actually going to go ahead and write R and R on here so I don't get mixed up. And I'm going to switch this top one around. So that's actually a group switch, which changes the stereochemistry. So this still matches the stereochemistry as it appears down below. And then this is going to turn into S. Now remember, this is the 5 carbon. And this is the 6 carbon here. And this is still the 5, and that's still the 6. So this particular diastereomer would be 5R, 6s. Yeah, and it does matter. I mean, I'll look. I grade based on your interpretation of that. Does anybody have any questions? Now, in the question it asks for a diastereomer. There's two. The enantiomer of this one would be the other diastereomer, so that'd be 5s6r. So the mirror image of the one we just drew would be the other diastereomer, but you're only asked for one. Does anybody have any questions? Okay, the last question is about whether it's meso or not. And in order to be meso, it would need to have a mirror plane, right through the middle here. But it doesn't, so it's not meso. None of them are meso. None of the isomers are meso. All right, does anybody have any questions? Any other questions about number 5? I still think one of the best ways to practice this is to do the quiz, the stereochemistry quiz. It's hard. I know it's hard. I know it's a hard quiz. Yeah. But occasionally what happens is people do it and they'll send me questions. Say, well, look, why is this S? Why is this R? And sometimes that helps. Sometimes, I don't know. Victoria, I'm going to put you on the spot here. Did that solve your problem when you were talking about getting a lot of them wrong because the priorities?
It's funny that I was applying the same logic over and over, but then I was getting 50-50 success rate and 50-50 failure.
But
I went back. Yeah, after you explained back, I went back to my mistakes and I saw that I just incorrectly assigned priority. That's all. And then everything checked out.
Yeah, see, so it worked for Victoria. She was actually able to sort it out because she noticed that she was getting them consistently wrong.
Yep.
So All right. Any questions? Any other questions?
So for the meso, it needs to be like exactly the same across like a horizontal.
Yeah. Across that. You see where I got the dot there, Courtney? Has to be exactly the same on both sides.
Okay.
But it doesn't have to be all of them have to be meso. It's just which it does ask if any stereoisomers are meso.
Okay, and then for meso, it would have to have the same like carbon chain and everything.
Yeah.
Okay.
The same arrangement on each side of a mirror.
Okay, perfect.
For determining if something is meso or not, can the mirror plane be vertical?
No.
Okay, it has to be horizontal.
It has to be horizontal through those two chiral centers. Yeah. No. Any other questions?
And you did just say that it's not a matter of rotating them. So if it had the same, obviously hydrogens would be at the top and bottom. But let's say it had the same carbon chains, but they were on opposite sides, same elements. That still would not be meso, or it would be?
It wouldn't be. No, it has to be an exact mirror image on each side.
Okay. Thank you.
Any other questions? Okay. All right, let's look at number 6 here. Okay, I don't think I've done this one before. I don't recall doing this one. So we look at the first one and we see it's TBU O minus and room temperature. So we know that's going to be strong base and room temperature. So for A, we're going to do a combination of substitution elimination. And this, let me be a little bit more clear here. So that would be the substitution product. You'll notice that I've bonded it through the O to the C that had the BR. That's kind of important. So if you did this, I would mark this incorrect. If you had this instead, because then I'd be wondering if you knew if it was bonded through the oxygen. So you've got to be real clear about that. Anybody got any questions? Okay, so the elimination products, that'd be 1. And this would be 1 as well. And I want you to understand that the other possibility that you might draw might be this one, but it's the same. It's the same. It's the same as that one above it. Does anybody have any questions?
When you find the same, one quick question, the bottom 2 that are the same, would a giveaway be when you try to find a main and you have 2 that have the exact same number of carbons, or no, you can have 2 mains sometimes?
I'd say it's possible to have 2 mains sometimes.
Okay.
Now, in this instance, no, I guess you do have 2 mains, right? I mean, neither of them are main because they both have 3 carbons connected to the C that has a double bond, right?
Right. Could you argue that the bottom one is more stable because it's part of a ring?
No. No, because the main criterion we use has to do with how many carbons are connected to the double bond.
The ring has nothing to do with it.
No, I wouldn't say so. All right, any other questions about A? Let's look at B. B is a strong nucleophile and heat, which means that it's a substitution and elimination as well. So the substitution product is just the N3 replacing the BR. And then there's just one elimination product, this one, which is the same as this one. Now, often people ask me, well, how do you know that it's the same? Well, if you can draw a mirror plane through the one with the BR, through the C with the BR on it, then you know you're going to get fewer answers than you might originally expect. Does anybody have any questions?
How can you tell which one is the main elimination product?
Well, there's only one elimination product.
Oh.
So there's no main to talk about. We good? Anybody have any questions?
Real fast, using that plane of symmetry on the BR, or that line of symmetry, excuse me, if we went back to A, after you eliminate the BR and start adding the double bonds, could you also see a plane of symmetry though after the BR, but before you start adding double bonds? And that's how you know?
No, I would just look at the initial compound with the BR on it.
Okay.
It's a little bit harder to see, but there is a mirror plane through that as well. You got to remember it's a 3-dimensional structure, not a 2-dimensional structure.
Okay.
Okay, let's look at C. Now C is strong base and heat, which is just straight elimination. Now there is no mirror plane in this one, so I'm expecting 2 products. Expecting this one with the double bond connected to the ring, and the other one where the double bond is connected out to the C that's next to the C of the BR. And in this case here, we would get a main. That would be the main. So that would be for C. And the main is the main because it's got 3 C's connected to the C double bond, whereas the other one has 1 C connected to the CC double bond.
Really quick, can you just count that? Those C's connected to the double bond one.
I'll circle them, okay?
Okay.
And over here, well, actually this one only has 1 C connected to the double bond. Right there. All right, is that okay?
Yep.
All right, does anybody have any questions? Okay. All right, number 7. Now I'm going to spend some time on this one. Now remember, we did do a lot of number 8 the other day, so I'm not going to focus too much on number 8, but if we have time, we will go through it, but we may not get to it because I'm going to really focus on number 7 here. Because there's really only 4 possibilities you can talk about. We've got endothermic or exothermic nucleophilic substitutions. One could be SN1 or SN2. So those are the only 4 combinations possible. Now this particular one is endothermic, and I know it's SN1, and my signal there is that we're dealing with the tertiary substrate. Is anybody having difficulty determining whether the reactant is tertiary or primary? Any questions about that? As long as you can figure that out, then you know automatically whether it's SN1 or SN2.
Would you say that it has to have 3 things on that C in order for it to be tertiary?
Well, you have to, specifically, Julie, you have to have 3 C's connected to the C with the BR to be tertiary.
3 C's.
Yeah.
So it doesn't matter what direction they're in.
No.
But it has to be that, they have to be connected to that C that the BR is at.
Absolutely.
If they're connected at a different C, it doesn't count.
See, that's why it's always easy to tell, right? Do you see what I'm saying?
Yep.
Okay.
But if the 3 C's, if there's 3 other C's over to the left, it doesn't matter. It has to be to that C.
It's that C, the C with the BR on it. That's the only one that matters. All right?
Okay.
Okay.
But Dr. Musgrave, can't S1 have a tertiary 2 as well? I mean,
what do you mean? I mean, SN1 is going to be tertiary only.
Oh, I thought this one was SN2.
No, it's SN1 because it's tertiary.
Oh, I'm sorry. I thought you said SN2.
All right, we good? Okay.
What is something else connected to that C if it's not 3 C's, but it's 3 other things?
Well, it'll either be 1 C or 3 C's, Julie. Okay. I can guarantee that. May lightning strike me down if that's not true.
Okay.
So when you're figuring out what the energy diagram looks like, it's always going to have energy on the y-axis and reaction pathway on the x-axis. So if it's SN1, it's always going to be a double hump structure. Now, is this one right?
This is wrong.
Why is it wrong? Why is it wrong, Victoria?
Because their products should be higher than their reactants.
How do you know that? How do you know that, Victoria? Are you some sort of witch?
No.
No? How do you know?
Well, it's endothermic, so we releasing.
Oh, it's endothermic. Oh, yeah.
Mhm.
That's right. Okay. Okay. So it should look a little more like this. There we go. So we'll have reactants and products. Now let me be real clear about what the reactants and products are of this process. Now it's a substitution, and we know that because we're told it is. So that's the reaction there.
Is there any possibility of question 7 being an elimination?
No.
All right.
No, it's always going to be either exothermic or endothermic nucleophilic substitution. May lightning strike me down if it isn't. Okay. So there you go, reactants, products. Any questions so far? Okay, it's asking for the activation energy, which is always going to be from the reactants up to the highest peak. And then you've got the products and the reactants, and the delta H is always going to be the difference between those two. Any questions?
Are there 2 EAs?
Well, no. There kind of is. I mean, there's an EA here as well.
But we don't have to label it.
No, because the thing is, if you can get over the first hump, it can definitely get over the second hump because the EA is smaller.
Okay.
All that matters is the rate determining step, or the slow step, which is the one with the higher activation energy.
What would you mark as the transition state on this diagram?
We haven't done it yet.
Oh, okay.
But the transition states themselves will be where I'm putting the arrows. So if there's going to be 2, this will be TS1, this will be TS2. But I haven't said what those transition states are yet. So we've already done A through C, and now we're actually going to draw the transition states. So let's look at what's going on. And I'm actually going to do the mechanism first because I think that's more helpful in this part. Sometimes people get the transition states and the mechanism mixed up. 1, 2, 3. But this would be the mechanism that I'm going to draw here. This is what's got the arrows on it. So the first step is the BR leaving. And I'm driving Julie crazy here because I'm changing the way I'm drawing stuff. I know she doesn't like that.
Do you want us to label that as the carbocation?
No, you don't have to. It's a C with a plus on it. I think it's pretty obvious. So that's the mechanism, a 2-step mechanism. And the carbocation, I think this helps, but I don't know. A lot of people don't really think of it this way, but I wish they did. But the carbocation is here at this energy well that lies in between the 2 humps. Because it's kind of like a low energy state or lower energy state than either of the transition states. Now, if you look at, if you're considering that little area in there to be the carbocation, the middle structure, then we can draw what the transition state looks like in accordance with what the arrow is telling us. This arrow is telling a story that the bromine is leaving. So that's what the transition state is doing in that specific step. So the transition state looks like this. Now, the 3 dots there are not stereochemistry. What they're saying is that the BR at this point, at the very top there here, it could either stay or go. It's at the cusp of leaving or going back to what it was. That's the transition state. That's transition state 1. Transition state 2, that's the N3 joining on. Do you see that? The N3 minus is joining on. It's that arrow right there that I'm pointing to. So that's what the second transition state looks like. So that's part D there. Does anybody have any questions?
Can you just read the markings around the middle stage of the mechanism drawing?
The markings. Oh,
well, I see the N3 negative is going to the positive, and what is that up at the top?
The BR negative.
Oh, okay, thank you.
It's the BR negative.
Showing that it's off.
Yeah, but that had left, right?
Okay.
In the previous step?
Yes.
Okay. That makes it a bit clearer.
Would we carry it through to the last stage?
No. When we do a mechanism like this, once you've talked about it once, you don't talk about it again.
Okay.
It's like it's left and it's gone at that point. We don't talk about leaving again.
That's okay. Gotcha. I noticed too on a lot of the keys in the transition states, they would add to the first transition state an N3 negative at the top in the corner inside the brackets.
It's not necessary. No, that's superfluous. I don't think it's necessary.
Okay, just do it as you've got it there.
Yeah,
okay.
It's not wrong, Rebecca. I don't think it's wrong per se.
Okay.
But it's just not really necessary.
Okay, got it. Thank you.
All right. Any other questions? Okay. I'm going to find another one on another test that is an SN2. So remember for this one, the only difference between this one and the exothermic, the only difference, and I mean this very sincerely, the only difference is that this product here would be below the reactant. That's the only difference if it said it was exothermic. Everything else would be exactly the same. Is everybody clear on this? That's why I don't see it as being necessary to do this example again as an exothermic, because it really is just going to be the same.
I actually have a really quick question. Do you want us to be drawing stereochemistry in the transition steps?
Not on the SN1, but you will have to do it on the SN2.
Okay, thank you.
Wouldn't where the heat is be different though? The line for the heat?
No, I don't think so.
So it's
you mean the delta H? No, it's still going to be between. It's still going to be between the reactants and products, regardless, Julie.
Okay, it would just be longer, or
it might be,
or it would be above.
It might be above, but it's still going to be between the reactants and products.
Okay.
So I still stand by me saying that. There you go. This one is definitely a SN2. So hopefully you can see the difference between SN1, SN2, and how you know straight off the bat that it was. Are we okay with this being SN2? So energy reaction pathway. And if it's SN2 and it's going to be a single hump. Now this one is endothermic again. Which means I draw it again so that the reactants and the products are organized in such a way that the products are above the reactants. The actual reaction itself, just going through and doing that. So I can be very clear about what the reactants and products actually are. It being a substitution. Do you like that, Julie? I like to tease you with doing this. I do.
That's okay, but I'm not going to write a large group on the thing. I'm going to write methyl.
Whatever. All right. I'm going to sneer at it, though. It's not going to warm my heart, Julie, if you write methyl.
I know, but you still have to mark it right because all these people...
Yeah, but I'll sneer at it.
Yeah, but I won't know it.
Know that I will. Yeah, you'll know. You'll know. So there you go. That's the SN2. Does anybody have any questions so far? All right, again, I'll do the mechanism for this one. Being SN2, and so it's a single hump process, it's going to be a one-step process. So both arrows are going to appear in the same structure. So that's what the mechanism looks like. One hump, one step. So the transition state is going to be reflective of the fact that it's occurring all at the same time. So this will be the transition state. There's only one of them. I'm just going to call it TS. And for this one, I will have to show the stereochemistry. So Jonathan, you had asked that earlier. I'm going to show the stereochemistry on this one. Because, it's important that that's what's going on. It wasn't important with the SN1, but it is important with this one. I'll leave it pretty much the same as what I'm doing here. So let's have a look. All right, so what's happening is that the SH is coming in, the BR is leaving, and the shape of it is such that the hydrogens on that same carbon, one will be coming out and one will be going in. The SH and the BR will have 180 degrees between them and it will be drawn as such. This hydrogen here is going into the page, this hydrogen's coming out. So that's what the transition state looks like for the SN2. All right, does anybody have any questions? And the only difference between this and exothermic, again, would be that the products would be below the reactants. Everything else in this problem would be the same. Okay, any questions? Any questions?
I have one.
Yeah.
Okay, so it's SN2 because it is
primary.
Okay.
But look, I mean, the thing is that there's a whole lot of background to this that I haven't even talked about while doing this example. Where can you find out that background? Well, you have to go back and watch the videos or watch the lecture where I talked about it. Okay, that's the bottom line. I mean, through this review, I haven't really gone into that much background because I've already done that. And the test is more about, well, I'll tell you what, it's a whole lot easier to get through the test if you understand what's going on than rather if you just memorize how to do the problems, which I know that's the route some people will take, but I can tell you this, those people will not do as well as the people who understand what they're doing. I can guarantee that. You might be able to think you can sort of just, I don't know, smooth your way through, but I don't think it's possible to do well on the test without knowing what the background is and and understanding the background, which is why I think it's worthwhile going back through the lectures or at least watching the videos, either one. All right, any other questions? I mean, there's more to it. Well, that's my point. There's more to it than it's just, yes, I know it's SN2 because it's primary, but there's a whole lot of other stuff for why primary goes SN2, which I haven't even talked about today, but I have talked about it ad nauseum in other fora. All right, any other questions? All right, well, it looks like we do get to go do number 8 today. So let's take a look. I'll do number 8 on this one. Have I done this one? I think I might have actually. Have I? Have I done this one? Can anybody? It looks familiar. All right. Maybe they're just beginning to all sort of bleed together and look the same. It's possible. That's a common complaint I hear from students. Everything looks the same. All right, this one's supposed to be an SN1 reaction. All right, so let's go ahead and do it. So I know that given that it's SN1, I'm expecting 2 products. And the 2 products are going to be one where it's going to not change stereochemistry, which means I'm going to do what I'm calling a direct replacement. So that'll be one product. And then there'll be another product as well, where the 2 of the groups are switched. And the ones that are switched will be the whatever it takes to get the lowest priority group into the back. The lowest priority group is the hydrogen. And I want it actually down here at the back. So what I'm going to do is I'm going to switch those 2 groups. I'm going to put the chain on the wedge here where the hydrogen was. And the hydrogen now is going to go down where the chain was. And the reason I did that is because I can easily get the priorities on this one. The priorities are going to be as follows: 1, 2, and 3, with the 2 going on the chain. The 2 going on the branched chain, with 3 going on just a straight chain. So I would call that, let's see, 1, 2, 3, that's R.
And just to be clear, no matter which 2 groups we switch, as long as the lowest priority group ends up in the back, we'll always get the correct stereochemistry? I
Yes,
mean, not stereochemistry, the correct RNS.
Yes, as long as you only switch 2 groups, Rebecca,
Okay.
and you don't rotate. You have to switch 2 groups. Because if this one is R, then the other one had to be S because we got to the R by switching 2 groups.
Okay.
And if that one's S, then the reactant had to be S as well, because we got to the one I'm pointing the arrow to by doing a direct replacement and not changing the stereochemistry. So stereochemistries don't change. So the name of this would be, let's see, 1, 2, 3, 4, 5, 6, 7, 8. So it's an octane, and it would be, this one here would be, S2-methyl. Let's see, 1, 2, 3, 4. 1, 2, 3, 4. 4-bromo octane.
They switched? 4-bromo 2-methyl octane?
Yes. Yes, that's right. I was just testing you to make sure that you were paying attention. Yeah, because of the alphabetization. Right, so that'd be 4-bromo 2-methyl, you're correct. 2-methyl octane.
Why don't we put a number on this S?
Because there's only one chiral center.
Okay.
I could if I wanted to. So if you want to, you can make it 4S and put in parentheses like that, or you can just leave it as S. Or you could even do it 4S without the parentheses too. That would be fine.
Can I ask another question?
Mm-hmm.
What happens if you're going to count numbers and whatever it is falls like right in the middle?
Then you could number it from either direction.
Right. You can?
Yes.
And it won't matter.
Right. As long as everything's getting the lowest number it possibly can, Julie.
Okay.
So, I mean, if this one here, for argument's sake, it ended up in the middle. There was an extra, let's say, 1, 2, 3, 4. This one has 1, 2, 3. So let's say there was an extra, can you see my cursor?
Yes.
Let's say there was an extra carbon here, right? Then the bromine would be in the middle. But I'd still have to number it from this side because of the methyl group to get the lowest possible number on the methyl group. Okay, so this would be S4-chloro. Methyl octane. That's one word. And this one would be R, yada, yada, yada. Same thing. 4-chloro 2-methyl octane. All right, does anybody have any questions?
I don't remember where I saw it, but somewhere the OH came in, and so the name was, it was an alcohol name.
I don't know. Oh, you probably, actually, I know where you saw that. You saw that on the sample, on the sample test. Yep. I won't give you any of those.
Okay, those were in the old days.
Yeah.
When it was more brutal.
Maybe.
I couldn't remember how we knew to do that, so I was going to ask.
Well, you wouldn't have known now, but you'll know in about a week.
Okay, excellent. Thank you.
Something to look forward to, Rebecca.
Yeah, I will be putting it on my calendar.
All right, any other questions? Any other questions? Let's see if we can hunt down an SN2 since we've got a little bit of time here. Let's see, maybe this one. Now, I don't like the fact that it's done this, but let me see if I can enlarge it. There we go, that'll do. All right. Not sure why it does that, but anyway. That's an SN1 as well. I'm going to do this as an SN2 though. All right, so just understand, I'm doing this one as an SN2, even though it's, no, it says SN1, but we're doing it as SN2. So I want something a bit different. All right, can you all see it? Okay, I'm going to assume that the answer is yes, you can. All right, so let's see. Maybe, CL minus. So we're expecting it to be a single product because it's SN2. And what's going to happen is I'm going to replace the BR with the CL. And I'm going to switch two groups. Whoops. I can't do that, can I? So I will replace the BR with the CL, but the hydrogen has to go into the back, which means the hydrogen needs to go where that ethyl group is. So I have to switch those. So I do two things at once here. I do a substitution and I switch two groups. And this enables me then to get these priorities. That'll be 1 for the CL, 2 for the branch, and then 3 for the ethyl group. So that would be, that'd be S, right? Yeah. So the name of the product here, let's see, so it'd be S. That would mean that the other one had to be R because I switched two groups to get to that point. And this would be S2 methyl. This is actually an example of one where the chlorine is in the middle, Julie, but I have to number it from, let me do S. So that'd be 2 methyl, 2 chloro, so 3 chloro. 3 chloro, 2 methyl pentane. And again, I think it's good to understand why these do what they do rather than just memorizing how to do the problem. And the whys all come from the background. Time and again, I find that the people who are successful with this class are the people who understand the background. And the people who fail tend to be the ones who are just trying to memorize everything. Bromo. It seems like it's easier just to memorize rather than actually understand, but it's an illusion. So that's how you do that one. Does anybody have any questions? Remember, that's an SN2, as if we're doing it as SN2.
Dr. Musgrave?
Yeah.
I always have a problem, like how do you figure out if it's starting in R or if it's starting in S?
Well, because when you're looking at the when you're looking at the product, we find out it's S, and that's how we know the reactant had to be R. You see, we're figuring out the R because we knew the product is S. And again, okay, that's the nature of the SN2 process. it switches stereochemistry.
Okay. Now, if it was an SN1, how would you
Well,
determine that?
then again, I do exactly the same thing as I did previously. Okay. I would figure out the product that had the lowest priority group in the back, know that that was, say, S, then the other one produced with it had to be R, which meant that the starting material had to be R as well. I mean, that's just what we did on the previous one.
Okay, thank you.
Okay. Does anybody have any other questions? We're kind of out of time here. All right, if you want to hang around and ask questions, you're more than welcome to. I'm not sure who was asking that question just now. Who was asking that question just now?
Brittany.
Oh, Brittany. If you want to hang around, Brittany, I can be more detailed about it. Okay?
Thank you.
All right. Anybody else have any questions?
Nope, thanks.
Okay. Well, I'll see you all later.
Bye.
Bye.
I'm going to stick around to listen.
Okay. All right. So Brittany is still here, so what I'm going to do is I'm going to do this as the SN1, and we'll see. So if I was doing it as an SN1, I'd know I was going to get two products, and the first product will have just a direct replacement without changing any stereochemistry. And the other product will have the lowest priority group switched into the back. And then we do the priorities, be 1, 2, 3. So that would be S. And then that would mean that the one I got that from, because it was involved a switch, that would be R. And since R was just a direct replacement, then that would be R as well.
Okay, that makes a lot of sense. I was just looking at it last night and I just could not figure it out for some reason.
You've got to remember that, per the background for SN1, R gives R plus S and S gives R plus S as well. And for SN2, R gives S and S gives R. I think that's important. But again, it's going back to the videos to explain why that is. And that helps, I think.
Okay.
Okay.
And then just one more question. So I was doing the cis and trans, drawing those. For the trans, does it matter which one you put as the dash line?
No, as long as one's dash and one's wedged.
Okay, because when I had drawn it, I just drew it differently than on the key.
No, that's okay. That's okay. But for cis, both wedge, both dash, either one.
Okay, thank you.
All right. Francisco, do you have anything?
No, just here to, just in case I catch something.
Okay.
I don't have anything else to do.
Hopefully you won't catch Rona. That's okay.
Odds are good. I work in a hospital.
Oh, that's unfortunate. Okay. All right. I'll see you guys later then. Unless there's something else.
Nope. Thank you, sir.
Thank you.
Okay, no worries. Bye.